Hello students, let's begin lesson 12, the definite integral, or just the integral. Previously we studied indefinite integrals, or antiderivatives, and those were functions. Here's a brief review by the way. Now what is the definite integral? That's different. That's going to be a number. Remember, the indefinite integrals were functions, but the definite integral is a number. But then, what is it? What exactly is a definite integral? Well, we're not going to define it precisely here because it's too hard. It's out of scope. I usually do it in Calculus 2 using the theory of Riemann sums. Here, we're going to cheat a little bit. We're going to take a graphical viewpoint and describe its property, and that's about it. Let's begin with a graph of a continuous function in a closed and bounded interval AB like this. And let's define the definite integral as a signed area like this, blue area minus red area. When the function value is positive like this, assign the plus sign, and the function is negative here, in other words, the y-coordinate is negative, then we assign minus sign. And then we add them all up. That's what we get. That's a signed area. Now, what if this graph had been a little bit more wriggly, going up and down more, so that we have multiple positive areas, multiple blues, and multiple negative areas, multiple reds? In that case, we just add them all up. After all, what we are after is the accumulation. So the total accumulation will be the total accumulation of all blues and all red, all put together. All positive, all negative, all put together and add them all up. And that's the definite integral. Now, speaking of accumulation, it's going to be a little bit easier to understand it using an example. So let's go to an example. Let's consider this as a graph of daily profit of your business venture, or more precisely speaking, a moving average of daily profit. Say 5-day moving average or 50-day moving average, things like those, so that we have a little bit more smoothened out graph, not the jagged graph that you see in stock market, those candlesticks and things like those. By the way, that's common practice in business. In order to do any kind of mathematics, you have to smoothen things out a little bit, so we consider moving averages and go from there. Okay, all right. Enough of preparations. Now let's analyze this graph. It looks like for about an year or so, or a little bit more than a year, looks like you had been losing money. Daily profit, or the average daily profit, had been negative. And then we have a break-even point around here, about a year or year and a half later, something like that. And then now your business is taking off and then you're making pure profit. Now here's a question. What is the total wealth or total profit you accumulated? You have to add up all the losses and all the pure profits together. All the losses and all the gains together. That's the total accumulation, and that's the definite integral. Make sense? So in summary, the definite integral is a signed area, not geometric area, and it measures the accumulation. Alright, so much for the definition, or rather a little bit cheated definition. And then let's go to some properties of definite integrals. First property, integral from a to a is 0. Second property, integral from a to b plus b to c is integral from a to c. You see, this number and that number are the same. In that case, we just go from first to last. First to last. A bigger font will be helpful. Here previously, starting and ending point are the same. In that case, 0. Here, from a to b versus integral from b to a, that's negative. Is there any good graphical descriptions of these? Well, the first one is easy to see. Integral from a to a can be visualized like this. And what you have here, we have a line segment. No region, so no area. Starting point and the ending point of the interval are the same, so we have a single point. So instead of a region, we have a line segment. And that area is, of course, 0. Let's compare this with original graph here. Here we have two different values, 0 and about 3.5. A and B values are different, so we have an interval, and we have a region, and consequently we have assigned area. Here we have nothing, so the area is 0. Next, this one is even easier to see. Remember, the definite integral measures the accumulation. An accumulation from A to B, that's brown, an accumulation from B to C, that's purple, and add them all up, we get total accumulation from A to C. Now the third property, this one is a bit harder to see, and most people view it as just a formula from A to B versus from B to A. Well, you can prove it rigorously like this, using the second property here, integral from B to A, and then A to B. So this number here, which is highlighted in bold, and this one I highlighted in bold, those are the same. So I get integral from B to B using the second property. But then again, integral from B to B is 0 by the first property. In other words, this one which I highlighted in blue, and the second one which I highlighted in red, add up to 0. So flipping red to the other side, we get blue is negative of red. That's a rigorous proof, complete algebraic proof. And if you feel okay about it, great. If you don't, then what choice do you have? You just have to memorize this as a formula. These two are easy to understand. This one a bit harder. Now, if you want to understand it in different graphical viewpoint, here's another approach. Go back to this original here and recall that how we assigned positives and negative signs. When y value is going up, positive y direction, then positive signed area. When we go down, negative y direction, then negative signed area. That's how I got plus and minus, depending upon the direction of y. Make sense? Now let's do the same thing to the direction of x. If you move from left to right, that's positive x direction. But if you move backward from right to left, that's negative x direction, and that's why you're going to get negative sign. Go back here. Integral from b to a, that's backward, moving from right to left. So it's negative of forward direction, a to b. That's another way to understand the third property. Anyway, we have all these three. Now, how about the next two properties? I can pull out coefficient, or I can separate integrals. Well, I've never seen anybody making mistakes on any of these properties, so I'm not going to bother too much about this. This one basically, if you add up before adding up, if you multiply k to everything and then add up, versus add up everything first and then multiply k later, that should be the same. It's a distributive property. And this one is commutative property. Add up first f and g and then accumulate, versus add up all f's, add up all g's, and then add those later. They should be the same. They're all additions. Addition is commutative and associative, so no problem there. In any case, I've never seen anybody making mistakes on these two properties. These two, worth remembering, they are a bit new. Let's see if we have one more topic here before example problem. The average value. I don't like this one very much because it's not that important for mathematical viewpoint. Maybe they're important in some other classes using integrals, but not here because this is just a formula. If you know how to calculate the definite integral, then all you have to do is multiply by 1 over b minus a. So that's how you get the average. No big deal. Now, in terms of graphics, well, here we go. The signed area, as you can see from the first picture, is the same as the area of this rectangle given by the constant function. And that constant function is the average value, 1 over b minus a times the integral. Okay, I don't want to dwell on it too long. Average value is not very important topics. And now let's go to an example problem. And let's do some estimations on definite integrals. Okay, all right. First problem, integral from 0 to 3 f of x dx. Integral from 0 to 3, it's around here. 0, 1, 2, 3, around here. So basically we are looking at 1, 2, 3 here, and then this part. And what's the area here? I can clearly see this is negative. And then how many squares? 1, 2, 3, 4, 5. Okay, and then a little bit half here, a little bit more than half there. Consequently, about -6. Let's see what I did in my answer key. Yeah, about -6. You see there are 5 rectangles, 5 squares completely captured. About a half, a little bit more than a half. Put together, I get about -6. Below the x-axis, so it should be clearly negative. And the real area is about -6.26 something, so this estimation was pretty good. Let's do it one more time. Integral from 3 to 6. How do you do that? So 3 to 6, so we have about here, that's going to be negative, and then 4 to 6, like this, and that's going to be positive. So it looks like we can estimate using these two triangles, negative area, positive area, and you know how to calculate the areas of triangles. That's going to be a good estimation. What do you think? Here we go, and that's what I did in my answer key. Red area here, and that's going to be a negative signed area because I went down, and then using the area formula of a triangle, about -1. And then here, positive. Again, using the area formula of a triangle, we can calculate, and it's about 5. So add them all up, I get about 4. And the real area is supposed to be about 4.23 something. So again, this was pretty good estimation. In any case, estimation problems are easy. If you get anything reasonable, you will get full credit. And of course, if you have finer grid, then of course the estimation will be a little bit more accurate. That too is something to think about. Okay, so much for section 1, and let's meet again in section 2. See you soon.